Hello and welcome to another GOM training webinar for the GOM software V8 SR1. My name is Markus Möller from the GOM training team. Sitting next to me are Thorsten Weikert and Frank Blankenburg from our software department. Thorsten will show you the new function live in the software, and Frank will answer your questions in the question and answer section. If you have any question, you can ask them in the Q&A section, and Frank will write down the answers for you. This webinar will be recorded as usual. You can therefore watch the webinar again later on or share it with your colleagues. We will show you at the end of the webinar where you can find the recordings. This webinar is about the function user-defined checks, which has been available since the V8 SR1 release. We created this function to easily enable non-standard checks without having to program a script. These may be applications, for example, for which checks on checks are required. However, you can also carry out calculations, like the calculation of a specific mass of an object. The function is seamlessly integrated into the software and is fully parametric. This means you can make changes to the parameters as you know and update the results by performing a recalculation. You can add a user-defined check to iInspect after the initial creation, and of course save it in a skin and therefore use it for future tasks. It is also possible, of course, to export and import the checks to make them accessible for other users or on other computers. The integration into a user-defined inspection principle is also supported. We already have prepared a video for you which explains how the user-defined check works. In the example, the angle between two radius entry points and a theoretical edge point is determined. Here we show you how you can use existing standard inspection elements to create a new check which doesn't exist yet. You can find the video at youtube.com/gommetrology. Then navigate to the playlist What is New V8 SR1. User-defined checks are included in all GOM professional software packages. You can use the function both in 3D metrology and 3D testing. And now I would like to hand over to Thorsten, who will explain the function for you in more detail. So, Thorsten, if you please.
Okay, Markus, thank you very much. So also from my side, hello and welcome to our training webinar, Customizable Checks. So, if you use our software, you'll use mathematics every day. It's your everyday work. You use it to check your all your relations. And now, maybe if you want some deeper mathematics here, we decided to implement the user-defined checks, as we call it. So. Basically, you want to inspect something like a point, you construct distances, you calculate fitting elements. All this is done completely implemented in the software, and you don't bother about the deeper backgrounds normally. So if you have to, you can now use these user-defined checks to help you calculate all your stuff you want to. So first of all, what is such inspection? It is the checking of a measured object regarding a physical quantity. So as already mentioned, we can check a distance for its length or a cylinder regarding its diameter, and you also have some other checks here. So I want to concentrate in the next few slides on the volume. So regarding the volume, we can, this is already implemented, we can later on calculate the mass of this object through it. So what looks like the check like in our software? It's represented by this menu here. So what are the parameters? What are the checks? What the checks do have? They first of all have a name to identify the check. Then they have a dimension and a physical quantity, a unit. This defines what's the check. And it also has a nominal value against which can be calculated the differences. So what does a customizable check look like? So, because it's fully integrated, it's implemented and parametric, so it might not be looking so different. So if we have a look here, it looks a bit more complex, but the basic unit, the basic parameters are the same. It also has a name, it has some unit and some nominal values. So what comes in addition are the additional input elements and values. You can now use variables to calculate your expressions later on. So you can here use input elements like already made checks in the software, use your inspections, or also use inputs like floating numbers or maybe also integers. And now we got the part of their actual expression. This is where the mathematics are done. Here you can type your expressions, enter your rules, and yeah, the basics like multiplication, addition, subtraction, division, they are implemented directly, and we have also some functions we can use there. I'll show you in some minutes. So if you're happy with a check and you want to use it repeatedly, or maybe use your colleagues to use it repeatedly, you can add it to iInspect, and these are saved, or then you can save it in your skin to make this usable for everyone. And you can also import and export your checks to maybe put it in a common folder or send it by email to your colleagues to already add it to iInspect again. And the last thing you have to do for this is to define the use-like behavior. So the iInspect is choosing which is proper for which type of element. So here you can choose that your checks behavior in the iInspect. But let's see how this works in the software. Now we start the GOM Inspect Professional. Let me start the recent projects. The standard GOM inspection part we can use here. Now turn on the mesh, make it visible, and if I select it, open the iInspect, and can check this for volume. That's nothing new, that's okay. We have directly the check, we have our value. And now on the same side, we can use the iInspect again and make a user-defined check. So now this shown dialog opens. First thing is to give an abbreviation. The name is also already checked. I'll choose M for mass. And then I can here define my input variables, my input values. So via this little button here, I can add input elements and values. And via the second button, we can remove them again. So first I'll define my variable, it's my volume. I can define the type here. As I said, we have different types with integers, floating numbers, and we've also our elements. It's a GOM element here. If I open this drop-down menu, my recently created elements are shown, and I can simply select the GOM measurement volume. The second part, to define the mass from the volume, I need the density. I'll call it rho. This will be a floating number. My plastics here have a certain density here, and now I can go on and enter my actual expression. To enter types here, I can use insert keywords, or I can insert another function. So let's start with the keywords. Got directly some examples here. I can use the actual from the mesh, or in this case, I want to use the v variable. It's the volume. Now, if I press the dot button, I can access the further properties of this element. So now I want the actual value, which is measured, and multiplicate it with my input number, the density. And I directly got the mass here as my result. It's also shown here in my label, the 3D. So now if I want to put it to inspect, I open the Properties Explorer, which go to check definition, and here I can do my last check. If everything's fine, that's okay so far, press OK and add it to inspect. So here I can type in a name for this check and the described use-like behavior. Here I choose the volume. I need the volume, so it should also behave like the volume. Press OK. Have a look here in my inspect. And first have to select the mesh. And here in my inspect, I got directly the check used here. As set, I can save it in the skin. Manage skins, save the skin. That's OK. Close. And as also mentioned, I can go to inspection, configure inspect. Here scroll down to find my mass check again, and can via these buttons I can export it, got a little file which I can send per email, put in the common folders to make it accessible for every colleague, and they can re-import these definitions on this little button. Okay, so far so good for the first example. What if it comes a bit more complicated? So here we got a shape of a profile, a blade profile here. So we made some thoughts about this with some simple conditions or simplifying conditions with only using Bernoulli. And these conditions on the left-hand side and some vector mathematics. We may assume some differences in the static pressure regarding the shape differences of the nominal and the actual section in these points. So therefore, after some calculations, we can get to this formula, which we now want to use to show the pressure differences from the geometry indicated from the geometry references all over this surface section. So this is done here. I also go to the software again, close the project, discard changes, open the blade project. It's also a demo project of us. Can use it here. And first thing I wanted to show is that if I now change the current skin to my user-defined skin, which I saved a minute ago, and then wanted to check my mesh here, open the inspect again. I see directly the check here. It's done. But first of all, I have to check it for volume because I need it for the calculation. When I try to check it for mass, you can see here the input dialog. I need to define my variables. Here's the drop-down menu again. And my density. Oh, that's wrong. Now it's changed. And take this one, got a new mass, and it's also implemented here. Okay, so just to make the label invisible. And back to my section inspection. The first thing I have to do here, just to make it easier for me, I want to have a look at my formula, which I want to type in, and now I can check the point, user defined, and type in my expressions here. It's the same, nearly the same dialog. We now have a nominal expression because I also checked the nominal element. I want the difference in pressure, so I call it dP. So therefore, the name has directly changed. We see it here. And now I can define my input variables again. Therefore, the incoming flow velocity is needed. This will be a floating number, say 150. And the next thing is the density again. Standard density of air at about 20 degrees Celsius. And now I can go on and type in my expression here. So first thing, input the density and divide it by 2. And now I need the square function here. This I find in my functions. We have here a variety of functions. These are general mathematical functions, rounding, conversion, trigonometric, many functions. And here under the general mathematical functions, I can see the power function, which I want to use to calculate the square of my incoming flow velocity. So the square, the exponent will be 2, and just type in V0 here. Okay, this works. So here's my name. I can choose it directly by typing. Good, so let's go on. Make everything right with these things here. So now I want to use the cosine function, the power function again. Sorry, so if I type in power, this is all directly recognized by the software, and the function is directly input. Now what happens if I type in cosine? This is also already recognized, so it's a built-in function, and you see it by this blue layout. And now I have to convert my 90 degrees to radians, because it's an angle calculation. So therefore, maybe we need some conversion functions. Okay, so here in the conversion functions, we find the red function, which converts a radian to radian. Type in 90 degrees, that's okay for me. And now subtract the arcus cosine. Maybe have a look at the trigonometric functions. And here it's also already implemented. So now I have to use the normal of my actual and the y part of this normal. So let's clear this, put in the actual point. Now use the dot again. Use the normal, can drop down it here, and directly get the access to the y part of the normal. So now I have all to close these all again to make everything right. Add the exponent, and if I have everything done all right, this value is directly calculated here. So as I said, I don't want only my actual expression, I want a comparison to the nominal. So therefore we copy and paste it down here. Standard Control C, Control V, and I have to just exchange the actual value with a nominal value. And here we got our nominal result and the actual result. And press OK, we got a deviation here. So this is my pointwise deviation regarding this formula. So we don't want to do it only pointwise, but also on the section. I have to add it to INspect. The name is OK for me, and I want it should be used like normal differences. I use normal, so it should also behave like this. Press OK. And after that, can choose my section, use the INspect, and find my user-defined check here again. Press OK. Again, need input variables. Press OK. Now, can change the legend again. Maybe use 1 sigma. Apply, close, and can now have a look at my section here in my inspection section, and can have a nice look here from the side, which shows the pressure differences regarding with the simplified assumptions all over my surface. Okay, so if there's even more to do, let's have a look on the next few slides. Now I got 2 more examples from our materials testing applications. The first is the determination of the slope of the elastic elongation part. Also called as a Young's modulus. It's a material parameter which is also often of interest for many materials. It's derived from tensile tests often, and here you have to define an area which an average is made for the for the elongation in the y direction, this part, and also the stresses shall be calculated here to use this stress strain curve to fit a line in. So as mentioned, I will show you how to choose these areas, make your checks on these areas, and also how to calculate your Young's modulus from the stress and strain curve. The second part, the second example will be the Poisson value. It's the negative quotient of y and x strain. So here you can, I will show you that this is a full field check, which you can directly calculate on your own. Okay, let's start here. Start the GOM correlate. Also here I've prepared a project. It's our testing object material. And here we have a point, we have a force input, and we have also the part of linear elongation in our timeline. So the first thing I want to do is to select an area of interest here around this point in the center. So I can go to Edit, Selection in 3D, Other Selections, and select inside Cube. So here already cube is done. So I want to make it on my point. So therefore press Ctrl and left mouse button so the point 1 is used here, and can maybe adjust the width or the length or whatever a bit. And if I'm happy with this, I can apply it, press close, and now inspect my surface component for strains in y direction. So I go to strains, y direction. So this is already done. I need another point. I need another name here. So it's called area. That's my area of interest. Press OK. And now I got the check only in this area. Go through here. You see only the valid values are in my selected area. So the second thing is I need to check my surface component for the stress, as I mentioned. I can find it in the same part. Check dimensions for stresses, and here you got the stress. Also here are some input values. Stress is force per area, so therefore type in my area and which kind of element should be used for the force. So this is constant all over the surface, that's by definition. And now I can use the averages in these areas to calculate my stress strain curve. So if I select the check here, open the iInspect again, I can directly check for the arithmetic mean of the whole surface. I have to select the whole surface first. Now my name is directly automatically chosen. Press OK. I can also do this with the XY area. Go to check, arithmetic mean. Here I also can select all, because only the values in this area are valid. So I can also press OK here and got my average only over this area. This is shown here now. Just want to make sure that these are displayed every time when I make them visible. And if I want now the diagram, I want my stress strain curve. Now it's the stress here, but it's over the index and not over the strain. So therefore, open it again, can choose my x-axis for the diagram here and use my strain value here. So now I have to recalc and got the check surface component sigma, so stress over strain check. So now from this check I want to calculate the slope of the elastic elongation in the elastic area here. So therefore I can now inspect my surface component, use iInspect again, and have now two options: make a user-defined check or a user-defined scalar. This is an indexed value, I'll show you in the next example, and this one is the scalar check. The Young's modulus is just a scalar, so I'll check for this now. So we got it here. First thing again, abbreviation. Name is changed again, and now I can choose my input variables again. So this will be the stress. Therefore I choose my stress sigma. I can use the strain. It's an element again. I will use my Y area average. And the last thing is elastic part. So this is not an element, but it's in stage range. Can also choose this type here. Got a drop-down menu. See my linear stage range. And that's okay. So now back to the expression. Edit again the keywords. But the first thing I have to do is to make sure that all stage values are calculated, and I need to construct a discrete data set, which is called the create XY graph here. So here it's a data container. I can put in my X and Y values, which are strain and stress. Therefore, I get in here, start to type strain, choose this one, but I want the value. That since it's in percent divided by 100. Also use the stress. Also use the value here. And now I can go on pressing the point. What can be done with this Y graph? I got directly some examples here. So make an average, derivative, or a fit line. Yeah, that's more or less what I want to do. But first of all, I want to restrict it to the stage range. So only in the stage range the values are used to calculate. Type in elastic here. And as already mentioned, we see here the fit line function. We can choose it. What yields this fit line function? It's the base and the slope of the fitted curve inside here. So I want the slope as my Young's modulus, and this is calculated directly here. Yeah, so this far. So if I now change my stage range maybe a linear was not until stage 15, but until stage 10, only my linear part. Everything will be recalculated again, and the value we see here has slightly changed. So it's fully parametric and it's implemented here. The second testing example I want to show you is how to calculate the Poisson's ratio on the whole surface of the specimen. So therefore, just quick, let me show this exclusively. We have a surface component, go back into I expect and check. Now user defined, because we want to check the whole surface. So therefore we need this user defined, not the scalar value, we want the surface based value. So we use this. First thing again, call it Poisson. Name is also done. Add the additional input elements. The first thing I need is the strain in Y direction. It's an element. And now I choose my surface. It's indicated over this icon. Here I can see the surface inspection and can also use the strain in X direction. Use the surface again, and now can begin to type my actual expression. So it's the negative ratio of these two values. Can use the strain Y, press the dot, and here I got the indexed value now. Choose this one, divided by strain X, use the dot again. Again, it's an indexed value. We can see it here, and as you see now, we have directly our feedback here. It's directly shown. All these values are parallelly calculated while I'm typing here. So I think this is pretty impressive. So here we got it now, and that's what it is. We got the surface based check and the Poisson's ratio in every single point here. Just to make it a little nicer, I'll change the legend a little and go through my project and see as all these colors are changing and how my Poisson's ratio behaves over the whole surface. So far, just to sum up, what is such a user-defined check? It's also a check type like every other inspection also. You can choose input elements and input values to calculate your results in the expressions. You can use scalar checks as well as full feed checks. All these values are possible. And you can choose your nominal type. This may come from the CAD. This can also be a fixed value, or this can be that can come from the reference stage. So you have wide possibilities to use here. Okay, so thank you very much for your attention. And yeah, now we have time for questions and answers. Thank you.
Okay, thank you, Thorsten, for your presentation. Yeah, really powerful feature, I think. I'm beginning to comprehend what you can actually do with it. So, just some further questions. Do we have, apart from the recording, which we'll be uploading later on, do we have any further documentation for this? So,
yeah, we have also some good direct helps here. So if I go back here again, choose it, go to maybe define a user-defined check scalar. Here you got this little question mark where we get to the direct help section. So here we can choose, here we can see some explanations, some direct help. We got some examples here. Also the elastic elongation as example is mentioned here. You can find some additional informations here, and yeah, it's a very powerful help here. So you can also click on these further informations, where you got some explanations of all your different functions. You got your general mathematical functions, rounding, conversions, which all these things do. These are described in these sections here.
Great. Good. Yeah. Something else. Is it the syntax you typed in pretty much looked like Python? Has it got anything to do with it, or?
Yeah, it's a bit Pythonic. So if you use the Python to use all these point and to get your results from your tokens, then you will be quick into this.
Yeah. I mean, what you typed in was pretty straightforward anyway. Yeah. So. And another Python question is, can the user-defined checks, can they also implement it in Python scripts, like to automate my workflows?
Yeah, for sure. It's implemented as a normal check also, so they can be recorded by the scripting functions, and they are used to use it to in your workflows.
Great. Okay. Well, we didn't have any other further questions, so I think we can wrap it up now. Mm-hmm. And so, like I said at the beginning, this webinar was recorded. You can find the recording in the manual and tutorial area at support.gom.com and on the GOM Metrology YouTube channel. So if you don't have access to YouTube, you can download an MP4 file from our support area. We will upload the recording for you tomorrow. And you may also simply subscribe to our YouTube channel, so you will then get notifications if we update some content. So it's really nice. I have it on my smartphone. This was the recording Customizable Checks. We will stay online for a while to answer any further questions you might have. Thank you for your interest. We hope you enjoyed it. We wish you a pleasant evening or day. Goodbye, and until next time.